So, a couple of keys of stoichiometry. Again, we need a balanced equation. And then we can use those coefficients in order to solve for one thing or another. Explaining to my first hour class, Chem 1 had a lot of, you have to write out the reactions. Do you remember that? Where we give you maybe the reactants and you even had to figure out what the products were. And there's a lot of that involved. A lot less of that is involved in AP Chem. Very common for an AP question to give you the equation on the top of the problem, and then there's a little story behind it, and then you have to answer some questions. In Chem 1 versus AP, again, we approach stoichiometry a little bit different. We spend a lot more time with writing the reactions and doing gram-to-gram stoich in Chem 1. In AP, however, given the equation, there's a lot of other variations we can do with stoich. For the most part today, though, I want to focus on what we did in Chem 1. For example, here's the equation for making rust. Iron plus oxygen makes iron 3 oxide, Fe2O3. I put in bold the coefficients, the numbers in front of each atom or molecule. Those are referred to as the stoichiometric coefficients. That's the important part when it comes to doing stoichiometry. So that equation says for every 4 irons, you need 3 oxygen molecules to react with it. That can make 2 iron 3 oxides. Remember, stoichiometry, however, is not based upon grams of one thing directly to grams of another. You have to convert to moles if you start with grams. Which, whenever you're doing any type of calculation in AP Chem, if you don't know where to start, turn something into moles. Sam, by the way, speaking of moles, you would not be allowed to wear that shirt when you take the AP exam. Did you know that?
I did not know that.
You cannot wear subject-specific clothing. Sam's got a picture of a 2 molar solution in the shirt right now. 2 moles inside of a beaker. I like it. These are the 3 steps we taught you in Chem 1. But to be perfectly honest with you, only going from moles of one thing to moles of another is actually considered stoichiometry. The first and the third step, that's just doing mole conversions. That's what we taught you in Chem 1. That's what you guys practiced over the summer maybe a little bit. And because the middle step is the actual stoich step, starting next class period, we can show you variations of stoichiometry. We touched upon it a little bit when we did the neutralization lab in Chem 1, where you did different titrations of acids with bases. However, we have to get full-blown into that next class period. And then next week, we have to add on to that with another application of stoichiometry, which is fairly tricky, called limiting reagent. All I have left for my notes is I'm going to go over a sample problem or 2. Okay? So when I see people done writing this slide, I'm going to show you the next slide. I don't think you should write the entire word problem when I show you the next slide. Okay? I'm going to actually flip the smart notebook and I'll show you how to solve it, and then just a shorthand way to kind of represent what was shown. But my hope is I spend roughly 10 minutes of notes on this. You guys spend roughly 15 minutes practicing it. It comes back to us a little bit. Maybe not all the way, but a little bit. Next class we'll practice it some more, and eventually we'll be like, oh yeah, stoichiometry, not a big deal. On the top here, if you want to write the equation, feel free to do that, because I'm going to do that on a problem underneath. The reason why I'd recommend writing the equation is you cannot do stoichiometry without a balanced equation. I had a couple first hour people trying to do that, where they started writing stuff out and they're doing 3 conversions, but what's going on with your middle conversion? Oh, it's a 1-to-1 ratio. How do you know it's a 1-to-1 ratio? You didn't write a balanced equation. This is a reaction we're actually going to do in the laboratory next unit. Calcium metal, an alkaline earth metal, is fairly reactive. Reactive enough that if you put it in water, it's going to create hydrogen gas. And it's going to make a base as well, calcium hydroxide, which I say is aqueous, although it is fairly insoluble, so that actually might create a precipitate instead, white cloudiness. Again, the question I have here was a very common Chem 1 question. If I have 11.5 grams of calcium, how many grams of hydrogen can be made? Don't worry too much about the added to an excess of water part of it. That's something that we're going to discuss more next week. That when I when I make the wording for a Chem 1 question, try to be accurate with it. However, I try not to confuse the Chem 1 students too much. So it's kind of a tricky line I have to kind of be on. So here's one way that I sometimes set up a stoich problem. There's that balanced equation that you just saw. To keep track of what I'm doing, underneath the calcium, I write 11.5 grams. Keep track of what I want to solve for, I put a question mark underneath the thing I'm trying to solve for. That way I didn't have to write out that entire paragraph either. It's just a little quicker way to organize my data. Any stoich problem that starts with a grams, you should convert it to moles. Again, pretty much any problem that we do starts with grams, you should convert it to moles. On the periodic table, the molar mass of calcium is 40.08. Connor, you have that one memorized? No. Do you have any of them memorized?
Last week.
Which is? Good. Okay. Had to teach metric to Chem 1 yesterday. Oh man, what a drag that is. And it took a lot of convincing, and probably wasn't effective either, of, hey, you got to show your work on a metric conversion. If I ask you going from milliliters to liters, I don't want you to just write down the answer. And some of them were like, well, I can do it in my head. And my response is, I don't care, because you can't do stoichiometry in your head, and I got to prepare you for that. Similar thing can be said with you guys right now. If I'm trying to go from moles of calcium to moles of hydrogen, it's a 1-to-1 ratio. And you might say to yourself, why in the world do I have to write 1/1? Not only can I can do that in my head because, yeah, multiply by 1, that's not hard. Divide by 1, that's not hard. It doesn't change the numerical value at all. My response is going back to what the College Board wants to see when you write an answer for their test questions. They don't want to just see an answer. They want to see a demonstration of understanding. And if you go straight from moles of calcium to grams of hydrogen, that's not actually possible. That's not a conversion that exists, of converting from moles of one element to grams of a different element. This conversion now allows us to cancel out the calcium top and bottom, just like the grams were canceled out prior, to leave with moles of hydrogen. And again, I know it seems like a waste of time, but quite frankly, you are going to be losing points from me. You're going to be losing credit from them. It doesn't take that long to just put that down. I do it. Last conversion. Hydrogen is diatomic, which means it's not just the mass of one H, it's of H2. That's its formula. And most of us have hydrogen memorized, Kylie. Yeah, 1.01. See, Connor? It didn't even have to be a whole number. She knew that. But we got to go 2.02 because the formula is H2. That gives me a final answer, by the way, 0.580 grams of H2. I carry 3 sig digs because the starting problem had 3 sig digs. What I can tell you is solving for grams of hydrogen is nice. However, hydrogen is a gas. And it's a gas that isn't very dense either. So solving for the mass of something that's floating around doesn't make a lot of sense. That's why I'm going to show you 2 other variations we can solve for, still using stoichiometry. Again, in Chem 1, we might not have considered it stoichiometry because pretty much we just told you going from grams of one thing to grams of another is stoichiometry. Stoich is just using those coefficients. That's it. I can convert from one element or compound to another element or compound. It's more than what we gave you in Chem 1, but Chem 1 simplifies stuff. Remember that octet rule that we hammered in Chem 1? Yeah, we don't have to abide by that. You're going to learn that in the 3rd unit. We simplify a lot in Chem 1, and then we take it to the next step in this course here. So, how about a different way of solving this problem? I have the same starting amount, 11.5 grams of calcium. But since finding the mass of a gas is complicated, maybe I want to know how many molecules of H2 is created. I can do the exact same first two steps. Convert your grams to moles. Use stoichiometry, although it's pretty simple stoichiometry and it's a 1-to-1 ratio, to go from moles of calcium to moles of hydrogen. I need to get to molecules. How do I do that? Six 6.02 times 10 to the 23rd. Avogadro's number. We actually will be using that number this year besides just, convert to atoms for no apparent reason. We use that number in electrochemistry. That's molecules of H2. 1.73 times 10 to the 23rd. Molecules of H2. So just a different thing that we could solve for the end. I'm going to give you one more example here to wrap things up. This equation, this reaction is something we're doing when we discuss gases in the second unit. Because we're going to create hydrogen gas, and we're going to do measurements with the gas, and we're going to figure stuff out about a gas. One of the things that you're going to learn next unit, no matter what gas it is, hydrogen, oxygen, carbon monoxide, think of any random gas there is. At standard temperature and pressure, so at a certain temperature and pressure deemed, standard, every gas behaves the same way. And in that, every gas occupies the same volume of 22.4 liters. So this is a known constant for things. If I flip back to the PowerPoint, my last slide mentions that. An ideal gas takes up 22.4 liters per mole. 1 mole of it, that's how much space it takes up. The reason why I bring up this point here is if I have an equality, like 1 mole is 22.4 liters of a gas, I can use that as a conversion. A lot of the math that we do in this class is conversions. There's not a lot of equation plug in and solve. Maybe a little bit, but not a lot. More of what we do is if we know certain equalities, we can use it to convert from one thing to another. And that's what I'm going to finish with today with our notes of just slightly different variations in stoichiometry. If I start with 11.5 grams of calcium, I want to know how many milliliters of hydrogen gas will be produced. And we'll say that's at standard temperature pressure at STP. First two steps, same as before, because it gets me to moles of hydrogen. Again, remember that idea of units canceling out. Grams on the top, grams on the bottom. Calcium on top, calcium on bottom. I'm left with moles of hydrogen. This is where I can use that equality that I mentioned about gases. 22.4 liters per mole. That way moles cancels out. And now I'm left with liters of hydrogen gas. And now it's time to be a Chem 1 student. How do I convert from liters to milliliters? 1,000 multiplied by 1,000. So the conversion is there's 1,000 milliliters over 1 liter. That gives me 6,450 milliliters of H2.